All right, good morning, everybody. Let's go ahead and begin. Well, I think maybe the first question some of you might have is when will the exams be graded? And that'll probably be sometime next week. I'll do it as quickly as I can, but I haven't started yet. So it'll be sometime next week. So this is one of 3 remaining lectures for the semester. We are really close to getting to the end. This is class 26, and so after Thanksgiving break we have 27 and 28, and that's it. Then our final exam is on Thursday, December 10th at 10:15. So I'll put that on the announcement slide for next time, but in case you're scheduling things out, our exam is 2 weeks from today. Now today we're going to continue into some new territory with Chapter 7, where we begin to account for energy losses, and it gives us some exciting capabilities to overcome limitations that previously have been a little bit problematic, and we'll talk all about that. But the remaining homework assignment that you've got this semester, homework 11, is due on Friday the 4th. And that's a departure from the normal pattern that we follow of having homework assignments due on a class day before class. So a little bit of extra time for homework 11. That'll be due, the last day of class is the 4th, the last day of all classes. You know, our final lecture will be the day before that on the 3rd of December. But you can take until Friday the 4th at noon to submit that assignment. Any questions before we move on to this new material in Chapter 7? All right. Excuse me. So far in the semester, when we have considered what's happening to flowing fluids, like if the water was stationary, we use the hydrostatic equation, and there really wasn't a lot more to stationary fluids that we did besides that. But when it came to forces that applied to moving fluids, we had to account for pressure forces acting over some distance. We had to account for gravitational forces, shear stress, and we're expanding our range of considerations now to the energy equation. And with that, we can begin to estimate the amount of power that's required to move fluids from place to place. For example, to move a certain amount of water from a treatment plant to a storage tank, or from a storage tank to someone's home. Or if we are thinking a little bit more broadly, you can use the energy principle to determine how oils and other industrial chemicals can flow through a pipeline and the amount of energy required to do that. And we're also going to look at some ways to estimate the effects of pipe friction and the energy losses and pressure decreases that come when there is a resistance imparted by the pipe to the flowing fluid. And when we begin to characterize that frictional force, then that allows us to understand how quickly water will flow through pipes based on the driving force. And so it could be that the pipe itself is inclined, and so the water is flowing by gravity from one point to another. Or it could be that there is a pump that's adding energy to the system, and that increase in pressure caused by the pump is what's forcing water through a fluid. And so determining the flow rates is an important kind of advantage of beginning to consider the effects of energy and energy losses. For those of you who are taking the fluid mechanics lab, you've already seen the effect of local losses, and so we looked at bends in a pipe and valves and different types of fittings. Not all of you are taking that lab, so we will talk about local losses here in this lecture as well, and how we can determine energy losses that occur at a single point rather than being distributed over a length of pipe. And so the energy equation, when I show it to you, is going to look kind of familiar because it has many of the same terms that Bernoulli's equation did. And so here on the screen is Bernoulli's equation, and what it relates is the velocity head and the piezometric pressure. And what we said with Bernoulli's equation is that when water is flowing through a pipe or a nozzle or from one place to another, that energy just changes form. It isn't necessarily lost, but for example, in the case of a pipe that's contracting down to a smaller diameter, because the velocity increases in the direction of flow, that told us that the pressure would have to decrease in the direction of flow. And what we did was we assumed that those 2 points where the transition occurred were relatively close together, because one of the big weaknesses of Bernoulli's equation was we assumed that it applied for a fluid that is inviscid. And so here, this list 1 through 4 is meant to bring your attention back to the assumptions and the limitations that we discussed for Bernoulli's equation. So I've already mentioned that the first of those is Bernoulli's equation assumes that it's applying to an inviscid fluid, meaning a fluid that has no viscosity. And the reason why we made that assumption is that here in Bernoulli's equation, there's no factor that accounts for energy loss or pipe friction between 2 points. And so to make sure that we got into as little trouble as possible for that, we said that we'd assume that 1 and 2, these locations, are relatively close together. Because the closer together they are, the less likely that there's going to be some friction losses that dramatically change the pressure compared to what Bernoulli's equation would predict. The second assumption, besides an inviscid fluid, was we said that it's an incompressible fluid, meaning that the density from one point to the other of the fluid is the same. And so that's a fine assumption for liquids, a little less good when we're talking about gases, which are compressible. The third assumption was that we're applying it along a streamline, and the fourth was that we have steady flow. So those were the assumptions, and the key weakness of Bernoulli's equation is that sometimes it doesn't actually predict the pressure change if there's been a significant amount of energy lost due to pipe friction, turbulence, or other factors. So what we can do instead is apply the energy equation. And I'll talk about each of these terms in detail on the next slide. But what the energy equation does is it's still relating energy at 2 locations. And it's for a viscous fluid. So not an inviscid fluid, meaning no viscosity. This time we're saying, sure, fluids have viscosity, and we're going to try and deal with that. What it also accounts for, there are additional terms on both the left-hand side of the equation, is a pump term, H sub P, and the right-hand side of the equation is the turbine term. And so that's what I mean when I say accounting for additional energy addition and extraction, is between 2 points where we apply this equation. If we say that location 1 is some point in a pipeline upstream, and location 2 is some point in a pipeline downstream, you can put things between those 2 locations like a pump or a turbine, and it'll either add or extract energy respectively. So we'll talk all about that here as we define the terms of the energy equation. And you'll notice that it looks a little bit different. There's alpha and a line above the V term. So let's talk about all of those factors here. So first of all, the line above the V, that means the average velocity. And Bernoulli's equation was talking about the velocity of flow at a single point. So we applied Bernoulli's equation, remember, along a streamline. So when I said the velocity at location 1, I might have used the average velocity like in a lab calculation, but what this equation really means is the velocity at the specific streamline in question. Whereas the energy equation already assumes that what you're going to put into it is the average flow velocity in the pipe at that location. And so you'd find the average flow velocity by the volumetric flow Q divided by the area. When you do that Q divided by A, the V you're solving for is the velocity across the width of the flow area. And so it's a spatially averaged flow velocity. Okay, so that's one key difference, is we're no longer saying that it applies just along a streamline. It applies from cross-section to cross-section. The next difference is that we say that between 2 points, point 1 could be here on the pipeline uphill, and maybe this is oil that's flowing through the pipeline, and then maybe location 2 is down here at this end. So H sub P simply says that if head is being added in the pipeline, if you have a pump running and the purpose of a pump is to boost the pressure. So if pressure is being boosted by a pump, then that's going to add energy. And so it's important that the H sub P term always appears on the left-hand side of the energy equation, because the understanding and the assumption with this is that water flows from location 1 towards location 2. So that means that 1 is the upstream location and 2 is the downstream location. And so if energy is being added, it belongs on the left-hand side of the equation, because what we're saying here with this equation, this formula says that the energy at 1 is equal to the energy at 2. Except for, it's really saying the energy at 1 plus how much energy is added by the pump is equal to the energy at 2 plus how much losses there were and how much energy was taken out through the turbine. And so HP and HT are not interchangeable. The pump term belongs on the left, the turbine term and the head loss term both belong on the right. Okay, so H sub P is the head supplied by a pump, and I'll show you the formula or the approach for how we could calculate that in Tuesday's lecture. But sometimes for now it will just be given. If we know that a pump is adding energy, then it would be expressed in terms of meters of head. Each one of the terms in this formula are going to have units of length. So P1 divided by gamma is going to give you meters. V squared divided by 2g will leave you with meters. And of course Z is in meters. All of these terms have units of meters. That's why we're able to add them together. H sub T on the right side, if energy is being removed between point 1 and point 2, then it's going to reduce how much energy is left over to go into the pressure, velocity, and elevation head terms. And so it's on the right-hand side because when you extract energy from a system, then that would effectively reduce the pressure at location 2. Head loss has two components. It has the local losses and friction losses. And local losses are those that are caused by energy loss or turbulence at a single point. Like if there is water flowing through some sort of a valve, then the turbulence that the water experiences as it flows through that valve, if it has to change direction, or if there's maybe the valve is a gate valve and there's a lip inside of that gate valve, or it's only partly open, there's going to be some energy loss as the water goes through that transition. And that localized decrease in pressure we account for here with H naught. And then the frictional losses that are distributed, meaning it's over an entire length of pipe, that's H sub F. And frictional losses are a function of the type of pipe that you're using, if it's rough pipe versus if it's smooth. And as you'd probably expect, a really smooth, let's say a glass pipe that has a very fine polished finish to it, that's going to induce less frictional resistance than a rough concrete pipe would that has like exposed sand. And so the rougher the pipe element, the greater the per unit friction losses are. Friction loss is also determined by the velocity of flow through the pipe at a particular time. The last difference between the Bernoulli equation and the energy equation is a kinetic energy correction factor. And the reason that we have to include a kinetic energy correction factor is because when you're utilizing the average velocity for the velocity head, it kind of underrepresents the true kinetic energy that exists in the fluid. And so if the water is laminar, if flow conditions are laminar, then you would use an alpha of 2.0, because what that means is that the average velocity, using that average velocity in the calculation of the kinetic energy, undercounts how much energy is actually there by a factor of 2. But laminar flow is pretty uncommon, and so more often we're using an alpha of 1.05 for turbulent flow. So here is a velocity profile that shows what the velocity would look like if conditions were laminar. And so at the center of the pipe, the velocity is the fastest because that's where it's furthest away from these boundaries where the shear stress is applied by the pipe to the fluid. And so here at the center, the velocity is at its max. And the kinetic energy correction factor essentially is just a way of comparing the maximum flow velocity to the average flow velocity. And because velocity is squared when you calculate the velocity head, the fact that some of the flow is going so much faster than the average just means that if you're using the average, you're undercounting how much energy is truly there as kinetic energy. And so like I mentioned earlier, for those rare cases where you have laminar flow, then you'd use an alpha of 2. But more of the time you'd use, because it's turbulent flow, an alpha of 1.05. And then that's close enough. This alpha of 1.05 is close enough to 1 that in a lot of cases people don't even bother including that kinetic energy correction factor. I wanted you to be aware of it and why it's added. And if you're really going for precision, then the kinetic energy correction factor would be included in calculations using the energy equation. But don't be alarmed if you just see the alpha kind of off the equation entirely. Sometimes the alpha term isn't even included because 1.05 is so close to 1. All right, so I'd like for you to get a chance to try this energy equation. And what we're doing in this example is we say that water is flowing from tank 1 to tank 2 because of an elevation difference in the water. So in tank 1, the water surface elevation, WSE, is 200 meters. And there's this conduit through which water can flow, and it goes to tank 2, where the water surface elevation is 190 meters. Now we know a little bit of information about the pipe. We know the length of the pipe, its diameter, and the reason why both of those are given is that water is going to flow at a faster rate if you have a larger pipe diameter. And so the amount of resistance that the flow experiences is partly dependent on the flow velocity and the flow length. So what I've given you here is an empirical simplified expression that is addressing how much head loss you can expect for this particular pipe. And so what we're saying is this is a formula that calculates the head loss as a function of pipe length and the flow velocity. Now we don't know the flow velocity. That's actually what we're trying to solve is V2. So this V is different from V1 and V2. V1 means the velocity at location 1. And location 1 for us is in the tank. And specifically it's at the top of the tank at the water interface where the water and the air is touching. That's location 1. So the velocity at that location inside the tank is 0. Because maybe the water level is going down very slowly in the tank, but not enough that it's going to have a meaningful contribution here in the energy equation. So we're going to say V1 is 0, because it's talking about the water at the top of the tank, and it's essentially motionless. The water is certainly moving through the pipe. There is a velocity in the pipe, and so V here, the V that goes into the head loss term, that means the velocity in the pipe. And then in this equation, the right-hand side, V2 is talking about the velocity of the water inside the tank. And so again, at the surface of the air and the water, where we know the elevation is 190 meters, we know the pressure of the water up at the surface is 0. So what we're trying to find here is what's going to be the flow rate through the pipe. And the key is to determine V, the velocity through the pipe, which is one of the terms in this head loss formula. All right, so let me pause for a second. And I've given you, I think, some pretty direct hints on what you should choose as location 1, what you should choose as location 2. And just by looking at the diagram here, we can see that there's no pump and there's no turbine. So both of those terms are also going to be canceled out to 0. So find Q, the flow rate. And what I'd like you to tell it in the units for that flow rate is how many cubic meters per second will be going through this pipe. We're stalled a little bit and not quite sure how to proceed. So let me pull up the PDF and show you what we got to do. All right. So it's, I think, a good practice to draw just a simple sketch of what we're looking at. So we've got one tank on the left with an elevation of 200 meters, and the water is flowing to the right where the elevation is 190. And it's going through a pipe that has a diameter of 0.35 meters, and we're told that the length of the pipe is 200 meters. And the problem gives us this formula for estimating the head loss. And so the 0.04, that would be some empirical friction factor that is talking about how rough the pipe is. And so the overall energy loss is going to depend on how long it is and how fast the water's moving through that pipe. And so what we're assuming by setting location 1 at the top of the water surface and the location 2 at the downstream water surface is that means that the pressure at both locations is 0, the elevation at both locations is 0. That's going to really simplify the energy equation quite a lot. The velocities are negligible even if the water level is going down ever so slightly, even if it's not strictly 0. And since there's no pump and no turbine, then here the energy equation is going to have both of those terms canceled out. So you can see that I've set the pressure head term to 0, the velocity head term to 0, and I think somewhere on here I say let's assume that alpha is 1, but we could have assumed it was 1.05. It wouldn't matter if we'd used that full, most accurate alpha correction factor because the velocity head term cancels out anyway, since the velocity in the tank is 0. Now the velocity in the pipe is not 0. V1 talks about the velocity in the tank at location 1. Okay, so what we have is what's driving the water towards the right is the elevation difference between location 1 and location 2. If the water is at 200 meters on the left and 190 meters on the right, that's why water is going to move through the pipe, is it's going to flow between the reservoirs until the two elevations are equal. So we've got a 10-meter elevation difference as the cause for the flow driving. And the only unknown in our head loss term is the velocity. So you can see rearranging that to solve for V means that the flow velocity is going to be 4.95, and then if we know the cross-sectional area of a 350 millimeter diameter pipe, we can calculate the area and then get the Q from that. So the flow rate is 0.476 cubic meters per second. So, any questions about that? Now, the slide down here at the bottom says, what would happen if Z1 was raised? So let me pose that question to you. If if the water level at location 1 was higher than 200? What if it was 210? What effect would that have on the flow rate if the elevation at location 1 was higher? The flow rate would increase. Jacob's right, exactly. So the driving force goes up, then the flow rate goes up. So yeah, that's the effect here. All right, so any questions about this example before we move on? Okay, a similar kind of problem, but let's say that now we measure the pressure difference on this pipe. The pipe is horizontal, and we measure a pressure difference some distance apart, and we want to know what's the head loss, and then if we're given this friction loss formula, then what would the velocity through the pipeline be? So consider this is a little bit different now. So this same picture, but now we're not saying Z1, like the elevation at 1 is 200 and the elevation at 2 is 190. I mean, that may be the case, but what we're going to use as location 1 and location 2 is we're going to apply those locations along the pipe. So it's kind of like in the lab how we've plugged in a differential pressure meter. This is very similar to that case because we have a difference in pressure of 25 psi, and so we don't know what the absolute pressure at 1 and at 2 is. We know the change in pressure between them. We know how far apart they are, and that's going to go into this head loss formula, H sub L. So where it asks here, what's the head loss between these 2 points, what we're trying to find out is the pressure difference is giving you an idea of the head loss. And so you can determine, for example, in this equation, if you're rearranging the energy equation and canceling out Z1 and Z2 because it's a horizontal pipe, and because V1 and V2 are the same, because it's the same diameter pipe, we don't have any information that the pipe diameter has changed, and so that means that the velocity at one part of the pipe is the same as at the other. Let me change this, by the way. So yeah, I guess it still flows from tank 1 to tank 2, but what I want to indicate here is that the pipe is horizontal. Let me make that a little bit more visually obvious, even though this is a side view. So the pipe is horizontal, and then the 2 locations that we're going to apply this energy equation at, here is location 1, that'll do, and here's location 2. Okay, so we plugged in our pressure gauge, and it's horizontal pipe. We measure a difference of 25 psi. Now, by the way, psi, of course, pounds per square inch. And so when we're working in traditional units, the gamma that should apply is 62.4 pounds per cubic feet. So that's asking for what is the force per unit volume. And so how many pounds of force per cubic foot? 62.4 in the case of water. And between these 2 points, there's no pump, there's no turbine, so both of those terms are going to cancel out. So what I'd like you to calculate is what's the head loss, and then once you have the head loss, what will be the flow velocity. Okay, let's take a look at this. For the unknown head loss, but we do know the pressure difference between the 2 points. So like I said before, I think it's a good idea just to do a little sketch of the scenario here where there's water flowing from one tank to the other, and by definition the amount of energy is going to be decreasing in the direction of flow. So that's why the water is going from 1 to 2, is because there's less energy at 2 than there is at 1. And so water is flowing downhill, so to speak. Even though it's through a horizontal pipe, if we were to connect the dots between this water elevation and that water elevation, it would give us a piezometric surface that indicates how much energy there is in the pipe at any particular location. So the 25 psi pressure difference, when we express that in terms of pounds per square foot, which is what we need to do since our unit weight is in terms of pounds per cubic foot, we have to multiply by 144 because there's 144 inches squared in a foot squared. So if there's 25 pounds in an inch, then there'd be 3,600 pounds in a square foot, because a square foot has 144 inches square. Okay, so that is the delta P. Now look at what we've canceled out in the energy equation. Location 1, remember, is here, and location 2 is here. So what we're saying is that in location 1, the elevation is 0, and it's also 0 at location 2 because it's a horizontal pipe. So there's no difference in elevation between 1 and 2. So that's why both of those terms are canceled out. Now we didn't cancel out the pressure head terms like we did in the previous example, because in the previous example we were saying location 1 was at the surface of the water where it's in contact with the air, and atmospheric pressure air relative to itself is 0. Now here location 1 is inside of this pressurized pipe, and so we don't know what the pressure is directly, but we can rearrange the energy equation to have P1 minus P2. And that's what we do. You can see in the line below, once everything else has been canceled out, we're canceling out the velocity terms because V1 equals V2. There's no pump, there's no turbine, so the head loss is essentially the change in pressure divided by gamma. So the head loss that occurs is due to pipe friction, and the way that that pipe friction is taking its toll is by reduced pressure. The pipe friction doesn't make the water velocity less at location 2 than it is at location 1. And this is a really important point. Think back to the lessons of continuity. In a pipe that's full, there can't be any storage, and so the flow into the pipe and the flow out of the pipe have to be equal. That means that even though the energy is decreasing, the velocity is the same here at 1 as it is at location 2. Something's getting lower because energy is decreasing, but what gets lower is the pressure. It's not losing energy in the form of a reduction in elevation. It's not losing energy in the form of a reduction in velocity. It's just exclusively a decrease in pressure. That is what we observe as the effect of pipe friction for this horizontal pipe. So if we now solve for head loss, it's the pressure change divided by gamma. So it should be 57.7 feet. Any questions about that so far? All right, the second part of the question asks, what is the velocity if we have this formula for the head losses? And so again, it's some friction factor term, a length term, velocity squared divided by 2g. So if that is the formula for head loss in this pipe, then, now I apologize, this is super sloppy. I just did it. For some reason I didn't already have this calculations in my notes, or somewhere. It's in a different location somewhere. But so here's our head loss formula. Rearrange it for velocity. So just algebraically, we're multiplying both sides by 2g and then dividing both sides by 0.025 L, and then take the square root of both sides. And so the velocity of the flow through that pipe, to cause such an enormous decrease in pressure between those 2 points, would have to be 31.9 feet per second. If it's 57.5 feet of head loss, and the length of the pipe is 145 feet, then that would be the velocity required to cause the pressure change that's observed. Okay, so any questions about the energy equation so far as we're applying it for these first two examples? Okay. When water's flowing through a pipe and the pressure is changing, then the water itself is doing work because the force that is applying, if you remember in the momentum, we said that if you cut a pipe where the fluid is pressurized, then the water on the outside of the control surface is pushing towards the inside of the control surface, and that pressure times area is acting as though it's an external force. And so a force applied over a distance, that is work. And so the force on the left-hand side of the pipe, if the water is flowing from 1 towards 2, remember in the direction of flow, the pressure is going to be decreasing because of energy losses. And so flow work is a way of accounting for the work that's being done by the water as the pressure is decreasing to overcome the resistance effect of pipe friction. And so the water is working to get through the pipe, and that's why we have to, why energy is used to move water from place to place, is the water is doing the work of overcoming the shear stress that's applied by the pipe to the water. So we can calculate the rate of that work, the power, by considering the time component here. And so if it's a pressure times an area, that's a force, and then the rate of the movement of the water, so change in length divided by change in time, so delta L divided by delta T is velocity. And so the flow work will be one way of calculating the amount of energy that's used, and the units for flow work are going to be watts. The reason for that, let me just bring that up. I've got that scanned here in my notes. Okay, so here's the units of flow work. If pressure is newtons per meter squared, velocity, of course, has units of meters per second, area has units of meters squared, then the pressure times the velocity times the area. Once we begin to combine things together, remember that a newton meter is the same thing as a joule, and then a joule per second is the definition of a watt. And so the amount of power that's used on a system where you're moving the water from one place to another can be estimated by the change in pressure between 2 points and the velocity of the water as it's flowing through the system. Another type of work is the shaft work. And we have in our energy equation both a turbine term and also a pump term. And so a pump does work on the flow. It's taking energy from outside of the system and putting it into the system by increasing the pressure. And so it's increasing the energy of the system. That's why it's on the left-hand side of the equation. The work is negative because the system is having work done to it. On the other hand, if you're extracting energy from the system, say at a hydroelectric power station, if the system is water that's elevated behind a dam, and then the pressure of that water as it flows through a pipe towards the discharge down below, if the pressure suddenly decreases because the water is acting on the surfaces of an impeller and causing that impeller to spin, then the work done that's done by the flow on a turbine is considered positive, because it decreases the energy of the system. And we'll account for both pumps and turbines next week when we begin estimating the amount of power in terms of watts that's required to move water from place to place, or when we calculate how much power can be extracted from a hydroelectric system like a dam. Okay, so energy, work, and power, sometimes those terms are used interchangeably, but what we've been talking about so far here in the energy equation, energy would be measured in joules, or in the energy equation, each of the terms here is set up so that they would have units of meters. And work is also measured in joules, but we think of like the difference between work and energy is that energy is used to perform work. Work is the task that's being achieved, for example, moving the water from place to place or spinning a turbine. And so the energy that's upstream, like the elevated water inside of a reservoir, the Z1 is that potential energy that's used to perform the work of moving water through a pipeline. And finally, power is when we add a time dependency here and we're finding the rate at which energy is being used or the rate at which work is being done. And so the power equation that we'll use in like hydroelectric calculations is the flow rate of the water, the unit weight of the water, and then the pump head or the turbine head. So here H sub P, this would be if we're calculating how much power is required to run a pump. But you could also find out how much power is coming out of a turbine by substituting in H sub T. And so if we look at this equation, the flow rate multiplied by the unit weight multiplied by the head, it's going to end up with units of watts. And we'll go through those calculations with our examples next Tuesday. Okay, one last example, just to close things out today. We have water flowing from this tank in the west towards the tank in the east. And there's pressure gauges along an inclined pipe section. The pipe itself has a physical slope, and so it's not horizontal like the last example was. And so Z1 and Z2 are going to be different now. They're not going to be equal like they were in our earlier example. But what we want to find out is how much head loss is between those 2 points. We're measuring a pressure difference of 86 kilopascals. But some of that pressure difference is going to be because of the elevation change, and some of that difference is going to be because of energy losses. And so we need to untangle how much of it is because of the elevation difference and how much of it is due to pipe friction. So we want to know H sub L, the head loss. So to do that, you should substitute in the terms into the energy equation. All right, so let me pause for a second and give you a chance to substitute in. Start thinking about if this is location 1 and this is location 2, then what would you use for each of the terms in the energy equation? And then also looking at this system, figuring out what to do with the H sub P and the H sub T terms, since we don't see either a pump or a turbine. All right, so let's see how we set this up to find out the head loss between the 2 points, because the pressure change is sort of a result of 2 independent factors. The pressure change that we're observing is partly because of the elevation difference, and it's partly because of the friction losses. All right. So I think it's a good idea to do a little sketch here. And you can see I've thrown one together. We've got a tank where we don't know the water surface elevation. That's not given at either location, but we don't need it because we know the pressure difference between the 2 points and the elevation between the 2 points can be determined on a relative basis because we know the slope of the pipe is 3% and the distance between them. And so if the distance between them is 545, and I guess maybe to be more specific, I mean that that's the horizontal component of the length of the pipe. because that's not the inclined distance, that's the horizontal distance, although with an angle as gradual as 3%, they're effectively going to be the same. The horizontal distance and the inclined distance will be essentially identical. But what that allows us to do is calculate a difference in elevation. So if we just say, let's let location 2 be our elevation datum, so that Z2 is 0, then Z1 is going to be higher. So it's at an elevation of 16.35. And the problem statement doesn't say anything about the pipe diameter changing. So V1 and V2 are equal. So V1 equals V2. No pump, no turbine. So lots of things are going to drop out of the energy equation here. The pump term cancels out. The velocity at 1, the velocity at 2 cancels out. The Z2 term is 0. There's no there's no turbine. So all that's left is that the head loss, if we're trying to calculate the head loss, it's going to be the change in pressure plus the elevation difference. So that's going to allow us to determine how much of the pressure change that we see is due to the elevation difference and how much of it is due to energy loss due to pipe friction. And so the head loss is 25.12 meters. So the elevation change is 16, and the pressure change, overall, if we think about how many meters of head that is, so 86 divided by 9.81, that's 8.8 meters of head difference due to the pressure change. So like if this was a horizontal pipe, then the pressure at 2 would be even lower than it is. But I mean, because you're losing energy in the direction of flow, but it's also downhill, and so the pressure measurement here of 86, it would be an even bigger difference if it was a horizontal pipe. But because it's vertical, some of the energy that you're losing due to pipe friction is made up for by the fact that location 2 is at a lower elevation. So if you just put it in, no, that's not the right one. We put it here into the formula, head loss 25.12 meters. Okay, well, that's all I have for you today. Remember this homework 11, it's available now if you want to get an early start. I think you can probably begin on the first couple of problems for that one. I'm going to be working through the exam. What I'll probably do is blind that so that you can't see your score until I've finished with all of them. And so I may obscure the final grade column in the grade book and the exam until I've got those all finished. And I'll send you an email. I'm not going to make you wait for 2 weeks. When I've finally graded all of them, I'll send out a message to let people know that the scores are available on Blackboard along with my comments. And so I hope you have a great Thanksgiving. We will pick back up again with a live virtual class meeting on Tuesday, December 1st. So that's it for now. I'll see you next time. Take care.